Alright, I'm basically running simulation of this transistor amplifier, which is pretty much that one out of the book they designed on, in your old 89 book or whatever that they designed, or had you design at the end of the common emitter amplifier section. So, but at any rate, came up with a lot of theories, and this it actually has it verified, because you look here across this capacitor. Okay, we got an 8.9 volt charge on it basically, but at your collector here, you have only 1.2 volts, and you can see the peak, it's 3.363 milliamps, which is going to be close to saturation, I presume, because you can see that we're not quite clipping yet, but it's getting close. So this actually ends up being the peak current is 584 microamps positive, and almost a milliamp negative. But at any rate, you can think of this whole thing like a charge pump. Okay, if I advance the simulation to where it's positive going, okay, and I guess that's about the peak. You can see that across this capacitor we've got about 8.9 volts, right? And you got a current going through it of about 585 microamps. And if you multiply 595 microamps times this resistance, it's 0.000595. I wonder if I should do this on the calculator just so it's more visible rather than doing it with my calculator. But at any rate, yeah, I'll give it a try here. I thought I had the calculator right here on the desktop somewhere. I guess I did that on the other computer, but I haven't done it on this one yet. There we go. Let's see, pin. No, it says unpin from start. Programmer calculator, I want a scientific calculator. I wonder how the graphing calculator works. But at any rate, it's .000. Yeah, I guess this isn't the best way to do this, because I have to take my cursor off everything, so that's not going to work. Anyway, so if you take 595 microamps, and multiply that times 8,500 ohms, it's 5.05 volts, which, voila, is, pretty much what our voltage is there, right? But, if you take You know, we got 18 volts, and let's say 8500 plus 6800, okay, and take 18 volts and divide it by that, you know, that's about 1.17 milliamps of current. So that can't be right. But the thing is that our, well, see, you know, this is the point at which the transistor is most fully turned off. Okay, so in other words, it's, you know, you can see it's only got 112 nanoamps going through it, so it's pretty much in an off or cut off point, you know, at this point. So you can see that it's clipping, you know, the waveform at cutoff. In other words, the transistor is all the way off pretty damn much, you know, very close to it, because the max current would be like 3 milliamps, but, you know, we're down to 112 nanoamps, and you can see it's 100, beta is 150 on this thing, by the way, but you can see it's got, you know, less than a microamp of, or less than a nanoamp of fucking input. So, you know, you can see the signal is extremely low, which right here somewhere, yeah, right there is our signal input. So, which right now is negative. So, but in any event, you know, the point is it's extremely low, and our voltage here across the base is only is only 970 millivolts. But, you know, we have a voltage here, you know, of about 600 millivolts. So, anyway, but so let's take 13.9. Because see, the thing about it is that under the circumstances, normally, you know, this would be, you know, a voltage divider, because again, it doesn't really matter that this capacitor has voltage on it or not. The problem is I kind of let it go too long, because you can see it's, since it's plateaued, I suspect that's affecting, you know, what the signal through the capacitor might be. In other words, I probably cut it off too late. Maybe. I don't know. Well, this is a current waveform, so it's, you know, it peaks at about, you know, 598 microamps. Anyway, I don't know, you know, if you take, you know, see this capacitor here has 8.7 volts across it. If you subtract that by, you know, from 18 volts, you end up with about 9.12 volts, which is actually the quiescent voltage of this, and I'll show you that in a sec. Well, in fact, well, anyway, I'll show you that in a second. But this nominally is, you know, 9 volts across the transistor, the VCE, but this ends up being about like 9.12 volts or something like that. And if you subtract, you know, you can see that 13.9 volts is where it's at now, but what matters is what's across this capacitor, you know, which you can see here. You know, it varies. The voltage across the capacitor varies from 8.6 volts to just a little over 9 volts, which is the quiescent point. And you can see the current variation here. Right now it's about 600 milliamps, but then it goes to negative 700. But at any rate, if you take, you know, this voltage from this voltage, you know, that leaves you with like, so it's 18 minus 8.78 Okay, and that leaves you with like 9.21 volts. Okay, but if you take 9.21 volts and divide it by 15.3K, which is the total resistance there, you get about 6.02 602 microamps, which is exactly where we got it right now. So that means basically, this essentially has the quiescent voltage charged on it. What I was a little surprised by is I was thinking, well, an AC signal should just pass right through this thing. I mean, right? There's supposed to be a transparent window, so I was expecting to be able to, because it seems like I did that earlier, that I took this resistor, added that, and I took it from 18 volts to figure out what the current would be, but that was like 1.2 milliamps, which is too big. But anyway, then you multiply that times this, and then it works out. But I think it does actually work out, just not... actually, I may have been doing that before when the waveform wasn't clipping. I'm not sure. But in any event, let's just say this does actually make some sense here, because it's this capacitor value. Now let me run this a little forward to the opposite peak. Alright, so you can see, right here, we got like, 897 milliamps, and we got about a minus 0.7 volt. You can see minus 0.7 volts. You can see the current 883, but the current is actually reversed now, because you can look at the voltage here, okay, and it's 1.3 volts. Now, as it so happens, if you realize this has, from just sitting there quiescently, a plus here and a minus here, right? So, but it ends up just like it currently has, with an 8.8 volt differential there. So that's the charge on it. But if you actually, subtract this from that, so you take, the 8.82 and subtract 1.312, that leaves you with 7 volts, right? So if you divide 8,500 by that, okay, that's 883 microamps is what it works out to. So, and of course you multiply that times 8,500. Okay, it works out to 7.508 volts, but it's negative 7.508 volts. I mean, so it works perfectly. And again, what's happening here is that when this transistor, is fully fully on, which is pretty much where we're at right now, because it's close to saturation. You can see where the waveform is just starting to clip. So this is like, close to saturation right here at 3.3 milliamps. But if you realize that, you got this plus and this minus, okay, so you can think of this capacitor like a battery, with this being the plus, but, normally that battery is sitting there with reference to the ground at 9 volts-ish. And, you can see it actually does get to a little over 9 volts. But the fact of the matter is, on average, it's a roughly 9 volt battery. But when you realize that, okay, you take that positive terminal and you drop it through the floor, basically the end of this is dangling, once you subtract this 1.23 volts from this 8 point something volts, it's dangling 7.5 volts below ground. Because basically this plate has been shifted down and this terminal went with it, so instead of being, negative, basically, or 0 volts, it's basically below ground. Now, that's kind of just the opposite, I think, of what was happening before, you know, because, you know, if you recall, you know, when we were sitting here at the peak, you know, we had, you know, 5 volts, you know, across the deal, but, you know, like I said, you had to subtract this voltage, whatever it was, you know, off of this to get the actual voltage that you need to determine that. But two, you know, you could almost take this 8.8 volts, and, well, because remember, under that condition, you know, the voltage, your current through the transistor is really negligible. So, but this capacitor still has a charge on it. Now it's dynamic, so, but again, it'll peak out, you know, by taking this voltage from this, and that's going to give it the peak current. But at the same time, it is actually charging the capacitor a little bit, you know, because that's kind of a byproduct of how these bypass capacitors work. So again, you know, in the other half of the cycle, you know, it's actually charging the capacitor a little bit. On this part of the cycle, it's actually discharging it a little bit. And it's that reason that this has a negative voltage across it, because it's actually coming exclusively from the capacitor. You know, more or less, that's what I'm saying. The current's actually in the opposite direction, so it's not the 18-volt battery, you know, going through the capacitor to supply it. No, it's just the opposite. The capacitor is basically completing a circuit, you know, through transistor land or whatnot to supply this, or maybe even through the 18 volts or what have you. But again, it does take into account the voltage, you know, that we're presently at, because again, that's a plus voltage, but, you know, this also is a plus voltage. So basically, it's sort of acting like a plus voltage here, because remember, you know, the transistor will still basically work, or try to actually have some, you know, allow some current, because there's some current going through it, as you can see. Well, right now there's a lot of current going through it. So that's what I'm saying. Yeah, right now it's in saturation. So, but that's what I'm saying. That's why this has got so much current going through it, and that's one of the other reasons too. You actually parallel these resistors to kind of figure these things out when you're trying to analyze it or whatnot. In other words, the collector impedance for AC purposes is actually this in parallel with this, and then you divide that by this resistor plus that little 25 millivolt divided by the current thing, but it's quiescent current that you figure that out on. But at any rate, you know, this capacitor is solely responsible for this negative voltage we have right now. You know, that's where the current's coming from and everything. It's pretty much coming from the capacitor. In other words, the capacitor is presently discharging. That's why right now, you know, we're in a trough. You know, we're going down to the minimal voltage that capacitor has across it. But eventually it'll go back to a little over 9 volts when it's charging up. So on the other half cycle, so we can run it to there. So, you know, in this half cycle, you know, okay, we got that 5 volts, but now, you know, the capacitor is starting to charge up, but it hadn't finished charging yet. And I get a big, oops, shit. But a big part of the reason it works this way you know, is because this thing's clipping. So, you know, you gotta keep that in mind. That has a bearing on it. I don't think we've quite peaked yet. Now the capacitor is close to its maximum voltage right now, but the point is that, you know, at this point, you know, that's when it's subtracting, as the transistor is still very well, actually it's well on its way back on now, but at any rate it's still very clipped. But at any rate, let me show you what happens at quiescent. So let's convert this to DC and reset it. It takes it a while to stabilize, because it's trying to charge up all those capacitors and everything. You see when it gets down to the picovolts, like we're at right now, it locks. See, at 3 picovolts. So, at that point, we can reduce the speed, and now I can go ahead and introduce a signal to it. Because you can see here first, before I do anything, that here, is the voltage. It's 9.14 volts. That's the quiescent voltage. The quiescent collector current is 1.3 milliamps. Okay, and this has 1.312 flowing through it, and you got 8.7 microamps going through, the base here. So, and of course, the voltage here is about 1.5 volts. So, versus that voltage, etc. So, but now let's go ahead and, and like I said, you can see at this point it's 9.14 volts across the capacitor. It's fully charged up. And there's just picovolts across the resistor there. But now let's go back to an AC waveform. Alright, so you can see a lot of the garbage going on here, but we're pretty quickly back to operating properly. So, but at any rate, let me go ahead and put this at a signal level where we're not clipping anymore, because I got intentionally set to to the point just right under where this clipped, because I wanted to see what the saturated voltage actually was reflected in the output. But oh, by the way, it's like I said, you should note that if you add you add these two together, okay, you got this minus 7.5 volts, and then you got this plus voltage here, 5.16. It's about 13 volts peak to peak. That's the actual range. And if you divide that by 2, all right, it's about 6.5 volts. But the gain on this is actually set to 20. So based on this plus the 30 ohms or so of this divided into the these two resistors in parallel, at any rate, works out to be about 20 is what the gain is set to. And that makes it a little insensitive to its beta. That's why you try to reduce the gain. Just like on an op amp, you don't want to really run open loop gain most of the time. You want to reduce it so that it becomes nice and linear. It helps linearize it and stabilize it. But at any rate, right now I got it turned up to intentionally clip it. But so let's get it down to a value that doesn't clip it. See, that's just barely clipping it a little bit. In other words, that's about what I found was the maximum signal amplitude I could put in there without it clipping the signal much at all, but you can see it just a little bit there. It's just barely clipping it. Now if you take it down to 200, well let's wait a second. But let's see. see 4.5 volts is the peak, you know, we have here. And you know, and basically minus 5 volts is the minimum. It may not have stabilized yet. Let me run it at high speed just to make sure, because normally this does kind of center. I mean, in other words, it should be equal amplitude above and below under normal running conditions. But yeah, I don't see the voltage varying here, so yes. Okay. So at any rate, but that's, you know, 5.8 volts or 4.8 volts. But this is still coming down to minus 5 volts, so that's interesting. But, well, remember though, it is partially clipped. That's what I'm saying. So I think that's a sign of that, you know, it's out of balance, so it's partially distorted. Okay, so let's run it at 200, which I know is below the distortion limit. Well, hold on a minute, I wanted to see something. Okay, so it's about the minimum point. Okay, that's at, you know, 3.9 volts is going to be the minimum collector voltage at 2.6 milliamps under the circumstances. So yeah, and then so yeah, 3.9 volts. Okay, and then, you know, 13.5. So it's, you know, about a 9 volt peak to peak variation. So but again, that's probably throwing our gain off a little bit. So, you know, because that's like 4. Yeah, 9.5. So 9.5 is like, you know, a little over 4.5 volts. At 4.6 volts or something like that. So if you take 4.6 volts, you know, and divide our maximum signal into it, which is oh yeah, which is right over here. Okay, right there. Yeah, it's minus 250 and plus 250, right? So we got it set. So 4.6 volts divided by 0.25 volts. Okay, it's a gain of about 18.4, so it's pretty close to the 20. Now let's take it down to 200, and that should get rid of all distortion for the most part. Okay, so now, you know, you can see it's a pretty well, you know, pure sine wave, pretty pure anyway. I guess we could do a spectrum thing on it and see. Running it so it can accumulate data. Okay. Yeah, so it's a pretty pure sine wave. You know, you do see some, you know, other peaks in there right around that, but you know, about 600 hertz is where we have it. But you know, there's a little distortion in it, but not much, because remember, this is the output. In fact, let me show you. You know, like we got a little more, you know, distortion. You can start to see some other sidebands show up. That represents the distortion that we're seeing. I'll take it to like half a volt. Okay, so now you're starting to see these bands grow. You know, you can see that it's becoming way more distorted. And if I take it to that, it clips the shit out of everything. You can really see the spectrum start, you know, getting a lot of crap going on in it because of the virtual square wave you have. But anyway, let's go back down to 200. It'll probably take a while given the fact that it kind of fucked everything up. But at any rate, yeah, this has got a pretty good sine wave. You know, it's fairly pure. So I'm just trying to wait for the numbers to stabilize. That's pretty much stable right there. Okay. Alright, so anyway, we can see it's, well, it's still, oh, yeah, so it's a little over 4 volts there, and, you know, because it's not perfectly balanced. Again, it's not perfectly pure, but, again, it's a lot closer than it was before, you know, like I said, at 3.9 volts versus 4.1, you know, it's a lot closer to being balanced, you know, in other words, an AC wave, but there's still a little distortion in it. It's not quite linear and everything, so, but you know, that's how it, you know, that's kind of how it works out. And like I said, let me okay, I think that's about the minimal peak. You know, it's, you know, 480 microamps, you know. But again, this is at 4.9 volts, and this is 9.06 volts. So, you know, if we take 9.06 and subtract 4.96, okay, that leaves us with 4.1 volts roughly, and you know, we divide that by our 8500 ohm resistor. Okay, it's 4. Okay. Well. Yeah. No. What? Oh yeah. Okay. Divided by 8500 ohm resistor. Okay. Yeah. It's you know, 482 you know, microamps, and we're getting 483 on this. So I mean, in other words, you know, the same principle applies, but it's more balanced. And then if you look at the you know, maximum signal is like 200 millivolts, right? So our maximum output, you know, is roughly 4-ish volts. So you know, it's almost perfectly at 20 as far as our gain is concerned. So but remember, the output impedance basically is just a 6.8K. The input impedance would be these two things in parallel, and then beta times our AC resistance. You know, the DC resistance includes this resistor here, but it's bypassed. So, but at any rate, yeah, that's you know, that's what the impedance basically is on this, and I think it worked out to be like I don't know, like 8K or something like that in the book. I forgot, but and something similar like 10K on the output. Well, I mean the output is 6.8K. It's the output impedance, but you know. But at any rate, you know, the point is that that's kind of how this crap sort of works. So, but basically, this transistor, you know, in the negative cycle, does actually supply the current exclusively for this resistor, and I've never realized that before, but I mean it does. It is the source, but you know, when it's on the other, you know, when it's down here, the capacitor is supplying it, but when it's up here, the capacitor is being charged up. So that's essentially what's going on. I mean, it is actually charging up. Well, in fact, let's run it and do the calculations. You know, because last time we did it was flat. Yeah, let's do the calculations on the actual sine wave here. Okay, so it's roughly, you know, the capacitor has 9.128 volts across it. Now, the current going through the capacitor, you know, is, you know, 440 microamps. So, but let's subtract 8 from 18, the value of the capacitor, which is 9.12. So it's 8.8 divided by 8,500 ohms. Oops, no. Divided by 15,300. Okay, so that'd be 579 microamps. So it doesn't actually follow here. That doesn't really jibe. So it doesn't behave the same way here it was behaving there, apparently. Well, let me run it and see, because we are a little off peak. What was that? 419. Yeah, the maximum current the capacitor ever sees is about 450. So again, yeah, I mean, that doesn't make sense. So it's about peak right now. Like I said, it's about 450 microamps, but so what am I doing wrong? At any rate, you know, it's not behaving like it was. Actually, I think part of the reason is this transistor is not as off as it was before, because remember, it was driven into saturation. Here it's not. I mean, it's still a pretty significant current, given the fact that we've got, you know, only 740, you know, it's about a third of the current's going through that. So that's probably throwing things off a little bit. Because again, you know, the transistor, basically, this is a maximum voltage it's going to see. It's not completely off. So that's why that way we were doing it before is probably not working, because we were pretty much saturating it. This was cut off. But it's not cut off here. So, you know, figuring things out on this side of the divide, you know, doesn't work as well. So apparently, yeah. But again, we were figuring the current's going to be higher than it actually is, but it's only, you know, instead of being 580 microamps, it's like 450 max. But a lot of that's going through the transistor instead, so, you know, it's sort of being shifted out, you know. So again, it's just not as easy to figure, you know, as it was before. That's why it's not really applying. Let's see, 6800 times 8500 divided by 6800 plus 8500 equals about 3.7K. So that's the actual AC resistance factor or whatnot. Essentially, it's RC basically. Don't know if that has an impact on anything now. This has a 5-volt drop across it basically, so it's 700 microamps. But, you know, like I said, this thing only has 450 going through it, and then the rest of it's going through the, yeah, it's going through the transistor, so it's a few hundred microamps there. So, but again, that's because we still got some quiescent current operating. It hasn't completely shut it off. So I'm not quite sure how you go about figuring that, but, you know, before, that's what I was trying to demonstrate, is that, you know, as a worst case, you know, this actually makes sense when you know, clip this from that, and then, you know, figure it out, it actually justified the voltage. But at any rate, you know, the point of it is, though, is that we're, you know, that's still basically how it works.